Welcome back to Physics 192. I'm Gerard Blanchard. Last time we introduced inductors into our circuits. The property of inductors is that they resist changes to the electrical current through the inductor. And the reason why this is that when the electrical current through an inductor changes, there is a self-induced electromotive force that induces a voltage difference across the inductor that's proportional to the change in current. Let's work an example of a circuit with inductors. In this circuit, a parallel combination of a 10 ohm resistor and a 7 millihenry inductor is connected in series with a 5 ohm resistor, a 6 volt battery, and a switch. There are several questions. The first two are, what is the initial current in the 7 millihenry inductor, and what is the final current in the 7 millihenry inductor? Meaning that the switch had been open for a very long time, and then at t is equal to 0, we close the switch. What is the current in the inductor? And then, after the switch has been closed for a very long time, an infinitely long time, what is the current in the inductor? And then finally, what are the voltages across the 5 ohm resistor and the 10 ohm resistor respectively immediately after the switch is closed? And what are the voltages across the 5 ohm resistor and the 10 ohm resistor after the switch has been closed for a long time? Okay, that's several questions, but we always start off by drawing our diagram, listing our knowns and unknowns, and please get started. Okay, let's draw our circuit. Here we have our 6 volt battery. This is the positive side. And we have a 5 ohm resistor. And we have a switch. We have a 7 millihenry, so that would be 7 times 10 to the minus 3 Henry inductor. And then we have a 10 ohm resistor. Okay, so the circuit is like this before t is, for negative time, before t is equal to 0. So in that case, the switch is open. The battery cannot supply any current to the circuit, so there's no current flowing in the circuit at all. So the current through the inductor is 0. And let me draw out some currents. We'll call this I1, I2, and I3. So I2 initial is equal to 0. So the current through the inductor is 0. We'll close the switch at t is equal to 0. So at t is equal to 0, we close the switch. And in that instant, the current through the inductor cannot change. The closing of the switch does not instantaneously change the current through the inductor. There's no current, so the current stays at 0 initially. It'll have to grow from there. So the initial current through the inductor is equal to 0. How about after an infinite amount of time has passed, I2 final? Well, okay, we'll have to consider that. We can figure that out from our Kirchhoff's laws. So for I2 final, we have to consider that the switch has been closed for a very long time, so that the current has grown to its final level and it's not changing. So the change in current through the inductor is 0, which is also going to mean that the voltage difference across the inductor is 0. And that means that there'll be no voltage across the inductor. So the inductor behaves like a wire, like a conductor, at t is equal to infinity. So this is t is equal to 0. At t is equal to 0, I2 initial is equal to 0. T final is equal to infinity. Well, we'll have to figure that out using our Kirchhoff's laws. And our Kirchhoff's laws tell us that I1 is equal to I2 plus I3. Okay. And delta V total is equal to 0, and we'll go once around this loop and once around this loop. So let's go around this loop. The switch is closed, so we can go here. We go up 6 volts, so plus 6 across the battery, minus 5I1, and then we close across the inductor, but we've said that the change in current with respect to time is 0, so the voltage difference across the inductor is 0, so it's like a wire. So there's no voltage change here, so we're back to where we started. I'll write plus 0, and that equals 0. So that tells us that 6 is equal to 5I1, or 6 over 5 is equal to I1. So I1 we figured out is 6/5, or what would that be? That would be 1.2 amperes is I1. Okay. Next we'll go around this loop. Delta V total is equal to 0. We'll go across the inductor, but the current is not changing, so there is no voltage difference across the inductor. So across the inductor we have 0. And then we're going with the current across down the 10 ohm resistor. And so that is 0 minus 10I3 is equal to 0, or minus 10I3 is equal to 0, which tells us that I3 is equal to 0. So the final current through the 10 ohm resistor is 0. And actually I'll mark these as final. I1 final and I3 final is equal to 0. And so then, using this equation right here, I1 final is equal to I2 final plus I3 final. That tells us that 1.2 is equal to 0 plus I3 final. So we figured out that I3 final is equal to 1.2 amperes. I'm sorry. No, I made a mistake there. This is I3. I3 is 0. So I1 is equal to I2 final plus I3 final, where I3 final is 0. So this becomes I2 final. Yes. So 1.2 amperes is equal to I2 final. So we'll write that. I2 final is equal to 1.2 amperes. So those were the first two questions we were asked. What is the initial current through the inductor? That would be 0. And what was the final current through the inductor? That would be 1.2 amperes. The other questions we were asked are, what are the voltages across the 5 ohm resistor and the 10 ohm resistor? Okay. To know that, we need to know the current through the 5 ohm resistor and the 10 ohm resistor initially. We've already established initially that the current through the inductor is initially 0. So that tells us that we'll go back to, let's see, for t is equal to 0, I2 initial is equal to 0, I1 initial is equal to I3 initial. Because any current that goes through this resistor must go through this resistor when I2 is equal to 0. So none of the current goes down here. It all goes this way. So the current through I1 and I3 are the same. So let's work on the voltage across those two batteries. So we're back to T initial is equal to 0. The change in voltage, well, let's work out what I1 and I3 are. We're going to go once around this circuit to figure out what I1 and I3 are. So we have delta V total is equal to 0. We'll start at this point, go around. That's going to be plus 6 minus 5 I1 minus 10 I3, and we're back to where we started, so that's equal to 0. So I'll write that out. Plus 6 minus 5 I1, all right, I1 initial, minus 10 I3 initial is equal to 0. And that would be plus 6 minus 5 I1 initial minus 10. I3 initial is the same as I1 initial, so I'll write I1 initial. I'll substitute in I1 initial here. And then that gives us plus 6 minus 15 I1 initial is equal to 0. Or 6 divided by 15 is equal to I1 initial. And that would be 3/5 or 0.6 amperes is equal to I1 initial. And since I1 initial is equal to I3 initial, that would say that 0.6 amperes is equal to I3 initial as well. Now from these, we can calculate delta V across the 5 ohm resistor. That would be 5 I1 initial. Delta V across the 5 ohm resistor initially would be 5 times the current through that resistor. And delta V10 initial would be 10 times I3 initial. And so that would be 5 times 0.6 and 10 times 0.6. So that would be 5 times 0.6. Actually, I made a mistake. Here. Let me go back and correct that. 6 divided by 15 is not 0.6, it's 0.4. Let me correct that. So 6/15 is 0.4 amperes. So I1 and I3 are both 0.4 amperes, not 0.6. So both of these are 0.4. Okay, so this is 5 times 0.4 and 10 times 0.4. So that would be 2 volts and 4 volts. So initially, at the moment when the switch is closed, we have a 6 volt increase across the battery, a 2 volt drop across the 5 ohm resistor, and a 4 volt drop across the 10 ohm resistor, so that plus 6 minus 2 minus 4 brings us back to 0. So the final current, the initial current through the 5 ohm resistor is 0.4 amperes. the initial current through the 10 ohm resistor is 0.4 amperes, which gives us a 2 volt drop across the 5 ohm resistor and a 4 volt drop across the 10 ohm resistor. Okay, how about the final voltage drop across the 2 resistors? We can do that pretty easily by inspection. T final is equal to infinity. Remember that we said finally there was no current through this branch of the circuit. I3 is equal to 0. Where do I have that? I3 final. I3 final is equal to 0. So if I3 final is 0, if there's no current through this resistor, then there's no voltage drop across the resistor. So delta V10 final is equal to 0, or in other words, it's equal to 10 times 0, which is 0. Delta V5 final is going to be 5 times I1 final. Well, we know what that's going to be, because if we go around the circuit, we have an increase of 6 volts. We have no drop across here, across the inductor, because the current's not changing. So we know that all the voltage drop has to go across the 5 ohm resistor. So we expect to see a 6 volt drop across this resistor. Well, 5 I1 final. I1 final is 1.2 amperes. So delta V5 final is 5 times 1.2. That would be 6 volts. So those were all the questions we were asked. What is the initial current through the inductor? That's 0. What is the final current through the inductor? That's 1.2 amperes. What are the voltages across the resistors initially? Initially, there's a 2 volt drop across the 5 ohm resistor and a 4 volt drop across the 10 ohm resistor. Finally, the voltage across the 10 ohm resistor is 0. And finally, the voltage across the 5 ohm resistor is 6 volts. And that is everything that we were asked to find. Those are all of our answers. Let's work another example. In the circuit, switch S is opened at t is equal to 0 after having been closed for a long time. How much energy is stored in the inductor at t is equal to 0? How long does it take for the current in the inductor to reach 0.5 milliamperes? Now remember that the energy stored in an inductor is 1/2 of the inductance times the current through the inductor squared. So U is equal to 1/2 Li squared. And also remember that the switch has been closed before it is opened at t is equal to 0. Go ahead and draw your diagram and think about the initial and the final condition of this circuit. Let's draw our diagram. Here we have a 6 volt battery, a switch which is initially closed, and then it's opened at t is equal to 0. We have an 18 ohm resistor, a 12 ohm resistor, and a 0.3 Henry inductor. Okay. So the first thing that we have to consider is what is the initial current through the inductor, and also we'll figure out what is the final current through the inductor. And it says how much energy is stored in the inductor at t is equal to 0. Okay, so U initial is equal to 1/2 times the inductance times the current, and that would be, let's see, we'll make this, once again, we'll make this I1, I2, and I3. So the current stored in the inductor would be 1/2 L I3 squared. So that's one thing that we're looking for. We want to know what that is. Well, we know what the inductance is, so all we really need to figure out is what is I3 initial. Wants to know the initial energy in the inductor. So what is I3 initial? Well, let's think about that. So for t is equal to 0, t initial is equal to 0. Initially, the switch is closed. So initially the switch is closed. At t is equal to 0, it's opened. But the current through the inductor cannot change instantaneously. So the current through the inductor will be the same as whatever it was when the switch is closed. So the current through the inductor at t is equal to 0 is the same as the current through the inductor with the switch closed. So let's work that out. We'll start here. We'll use our delta V total is equal to 0 to go around this circuit. That would be plus 6 minus 12 I3. And then if the switch has been closed for a very long time and the current is constant again, that'd be I3 initial, and the current is constant because the switch has been closed for a very long time, then the change in current divided by the change in time is 0, so there's no voltage drop across the inductor. If the current is constant, there's no voltage drop across the inductor. It's just like a wire. So that would be plus 0 is equal to 0. It says that 6 is equal to 12 I3 initial, or 6 divided by 12 is equal to I3 initial, or 0.5 amperes is equal to I3 initial. So the initial current through the inductor is 0.5 amperes. So we can actually calculate the energy now. U initial is equal to 1/2 times the inductance, which is 0.3, times I3 initial squared, which would be 0.5 squared. So U initial is equal to 1/2 times 0.3 times 0.5 squared, and that is 0.0375 basic metric units of energy, which are joules. 0.375 joules. So the initial current through the inductor is 0.5 amperes. Once we open the switch, we disconnect the battery from this circuit. Current will continue to flow around this loop, but it will decrease over time. And in fact, when we go infinitely long, so T final, T final is equal to infinity. So after an infinitely long time, the current through the inductor will have dissipated in this circuit. So I3 final will be equal to 0. Because after an infinitely long time, there's no voltage change across the inductor. The voltage change across the resistors depends on the current. But in order for us to get a total change in voltage across this circuit of 0, then those two currents also have to be 0. So after an infinitely long time, the current will be equal to 0. And then we were asked at what t is the current equal to 0.5 milliamperes. So for what t is I equal to 0.5 milli, so times 10 to the minus 3 amperes. So for that, you'll have to go back to your equations for the current through an inductor. And that equation is T is equal to our time constant tau times the natural log of I initial minus I final over I minus I final. And tau, remember that tau is equal to L over the equivalent resistance to the current that flows from the inductor. I initial minus I final over I minus I final. The equivalent resistance, once we open the switch, the circuit only consists of the inductor, because this branch doesn't count. The circuit only consists of, because this branch isn't connected anymore once we open the switch. The circuit will consist of only the inductor, this resistor, and this resistor. So an 18 ohm resistor and a 12 ohm resistor. And the current, whatever current flows here, has to turn up here and go through here. So since no current can flow down this branch because it's been disconnected by the switch, the 18 ohm resistor and the 12 ohm resistor are in series. So they have an equivalent resistance of 18 plus 12, which would be 30. So what does that give us? It gives us T is equal to L, which is 0.3 henries, divided by R equivalent, which is 18 plus 12, times the natural log of I initial. The initial current through the inductor is 0.5, minus I final, which is 0, over the current that we're interested in, which is 0.5 milliamperes, so that would be 0.5 times 10 to the minus 3, minus I final, which is 0. Okay, and all we have to do is calculate that. So the time is equal to 0.3 divided by the quantity 18 plus 12 times the natural log of the quantity 0.5 divided by 0.5 times 10 to the minus 3. That's the 0.5 milliamperes. And what do we get? We get 0.0691 seconds. So the current goes from 0.5 amperes to 0.5 milliamperes in about 7/100ths of a second. So there you have inductors. The current through an inductor cannot change instantaneously. It only changes exponentially. And the reason for that is whenever the current does change across the inductor, there is an electromotive force that resists that change. So the current through an inductor cannot change instantaneously. It changes exponentially with a time constant equal to L divided by R, or the inductance divided by the equivalent resistance. We're now going to introduce another component, the capacitor. And the property of a capacitor is that it resists instantaneous changes to its voltage. And this causes similar but slightly different behavior. The similarity is that the voltage across the capacitor can only change exponentially with a time constant, which we'll get to soon. There are two common symbols for a capacitor. The first, which is the one that I'm going to use, is simply two parallel lines. So in this symbol, the two parallel lines representing parallel plates have wires representing the conductors coming into the top and the bottom plate. Another common symbol for a capacitor has one parallel plate and one curved plate. You may see either one of those. I will use the parallel plate representation. The change in voltage across a capacitor is equal to the charge on the capacitor, Q, divided by the capacitance. So delta V across a capacitor is equal to Q divided by C, where Q is the charge on the capacitor and C is the capacitance. Charge is measured in coulombs. A coulomb is also an ampere times a second. So that's related to current. The capacitance is measured in units of farads, F-A-R-A-D-S, symbolized by a capital F, and a farad is a coulomb per a volt. And you can see that that's what it has to be to make your equation, delta V is equal to Q over C, come out right. The voltage is higher on the positive side of the capacitor, and like inductors, capacitors store electrical energy. The electrical energy U stored in a capacitor is 1/2 the capacitance times the change in voltage across a capacitor squared, or U is equal to 1/2 CV squared. What is the physics behind the equation delta V is equal to Q over C? Well, inside of a capacitor, what you basically have are two parallel plates with a gap in between them, like in this diagram. We put a positive charge on one plate, plus Q, and a negative charge on the other plate. The charge cannot cross the gap, but an electric field does cross the gap. An electric field extends from the positive plate to the negative plate. The electric field depends on the charge that we put on the plate and the area of the plate. So the electric field is 4 pi times K times the charge that we put on one of the plates, the positive charge that we put on the positive plate, divided by the area of the plate. We encountered that equation before. And so if there's an electric field pointing from one plate to another across a certain distance, then there is a voltage difference across the plates. Remember that the voltage is equal to the electric field times a distance. And so that gives us our relationship where the voltage across the capacitor depends on the charge Q and on the dimensions of the capacitor, the area and the separation of the plates. All of that gets wrapped up into our capacitance C. So the change in voltage across the capacitor depends on the charge that we put on the capacitor divided by the capacitor's capacitance. The electrical current is the rate at which charge is deposited on the capacitor. If we have an electrical current going into the capacitor, then that is bringing positive charge to the positive plate of the capacitor and taking negative charge away from the negative plate. So Q is getting bigger if we're charging the capacitor, or vice versa. If we were to run a current into the negative plate of the capacitor, that would bring positive charge to the negative plate and take positive charge away from the positive plate, which would decrease the charge on the capacitor. Now, note that when we refer to the quote-unquote charge on the capacitor, we're referring to the charge on the positive side only. The actual total charge on the capacitor is 0 because we have the same amount of positive charge on the positive plate as we have negative charge on the negative plate. So the charge on the capacitor, the positive and negative charge on the two plates, is always balanced. So the actual total charge in a capacitor is always 0. But when we speak about the charge on the capacitor, then that's really just shorthand for the amount of charge on the positive plate of the capacitor. And finally, when the charge on a capacitor has reached its final value, when the charge is not changing, so if the charge on the capacitor is not changing, then the current through the capacitor must be 0. So when the capacitor is at steady state, when its charge is not changing, then the current through the capacitor must be equal to 0. So how do we deal with circuits containing capacitors? Well, we use Kirchhoff's laws to calculate the initial voltage across the capacitor from the initial circuit, and so the circuit at t is equal to 0. And then we calculate the final change in voltage from the final circuit, or the state at infinity, so after an infinite amount of time has passed. We calculate the time constant, tau, from the final circuit. The time constant is equal to the equivalent resistance times the capacitance. So tau is equal to RC, or R equivalent times C. And in between 0 and infinity, we calculate the current and voltage from these equations. The change in voltage across the capacitor is equal to the final change in voltage plus the quantity initial voltage minus final voltage times e to the minus t over tau, or delta V is equal to delta V final plus the quantity delta V initial minus delta V final times e to the minus t over tau. So once again, the voltage across the capacitor changes exponentially. The current, the absolute value of the current, is equal to the initial current times e to the minus t over tau. So the current into a capacitor decays exponentially. And then we can invert these two equations to find time using time is equal to tau times the natural log of delta V initial minus delta V final divided by delta V minus delta V final. So delta V is the voltage at time t, so an intermediate voltage between delta V initial and delta V final. And finally, the time is equal to tau times the natural log of the initial current divided by the current at any time times the equivalent resistance. So these are the equations that you will use to find the voltage and the current at any intermediate time between t is equal to 0 and t is equal to infinity, or to find the time for any intermediate voltage and current. Next time, I'll start with a demonstration. Just as I did for the inductors, I'll show you a demonstration of how capacitors work using my simulation. And we will start to work some exercises so that you can apply these equations to circuits with capacitors. Until then, think physics.